Hi guys, Miss Miller here. I am recording the presentation on hearing. At this point, you should have your Unit 8 Waves Day 3 Hearing Notes sheet. If you don't have that out on your table, go ahead and pick one up now. And I'd like you to take a look at the warm-up. The warm-up is going to ask you to match the standing wave, so 1, 2, and 3, with the instrument A, B, and C. So I'll give you a moment to try your best on that. So the answers here, I'm going to go a little bit out of order. Instrument C, so that person is blowing into a water bottle that is open on the top, obviously closed on the bottom, and it has different amounts of water in it. That would match best with waveform 1, standing wave 1, where you have closed on the bottom and you have open on the top. For instrument B, that's going to be the xylophone. The best model for that is going to be waveform 3. So this models a closed end and a closed end. You can imagine that when the wave gets to the end of the xylophone key, that it bounces back as if it were a closed end. And that means that instrument A is going to match with waveform number 1. Waveform number 2. This is a pan flute, and this particular pan flute must be open on the top and on the bottom. There is a way to make pan flutes that are open on the top and closed on the bottom, but by process of elimination, that must be our answer here. Okay. So I wanted to bring this up. This is going to be our section on light waves. So I know that we've been talking about sound waves for a good portion of this unit, but I did at least want to dedicate a little bit of time to light waves because they are important as well. So while sound waves are longitudinal, light waves are transverse. And what you see on your paper is called the electromagnetic spectrum. Now, in the very middle of the spectrum, you'll see the visible light. You'll notice that visible light is actually a really small portion of all of the light that's out there. Just think about that for a second. Of all the light that exists in the universe, we can only see a very small amount. There's infrared light. This could be like if you're watching ghost shows and they use an infrared camera and they see a handprint and claim it's a ghost. It more or less communicates heat signatures. You have microwaves, quite literally used in microwaves. Radio waves, obviously where radio signals can come from. On the other side, you have ultraviolet light, ultraviolet mainly coming from the sun. Interesting fact, scorpions will actually glow under ultraviolet light. You have x-rays, obviously you have the application of being at a doctor's office and getting an x-ray. And then you have gamma rays, which are going to be a really high energy light, often made from really big cosmic events. They're quite literally called gamma ray bursts. So you can see on this kind of left side of the spectrum, you have shorter wavelengths and higher frequencies. On the right part of the spectrum, the other side, you have much longer wavelengths, radio being the longest with therefore lower frequencies. You can look up above the window and you can see this electromagnetic spectrum as well. I should warn you that above the window, the spectrum looks backwards. So gamma rays are on the right and radio waves are on the left, and that's totally fine. You'll actually see both versions of the spectrum. It's just a preference of which way you want your long and short wavelengths to be. So transitioning back to sound waves, we of course know that sound waves are longitudinal. And that really comes from the compressions and rarefactions of the air molecules that those sound waves are pushing around, and eventually those pressure waves get to your ear. So this does mean that if you were in outer space where there aren't any air molecules, then sound would not be able to carry over to your ear. So all of those Star Wars films and whatnot where there's an explosion in space and you hear the explosion, it would actually be completely silent. Now, when it comes to sound, higher frequencies are going to translate to be higher pitches. Vice versa, a lower frequency is a lower pitch. So with your instrument project, I said you needed 8 different frequencies. That's the equivalent of saying you need 8 different pitches, 8 different notes. Larger amplitudes are going to be louder sounds, and vice versa, smaller amplitudes correspond to smaller or quieter sounds. So we're going to zoom into your ear now. We're going to talk about how your ear takes in those pressure waves, and then what does it do to actually make your brain interpret what you're hearing. So your ear is composed of kind of 3 different sections. You have the external or the outer ear. This is like everything that you can see on someone's ear. Its entire purpose is to collect sound and then channel it into the next part, which is the middle ear. The middle ear. The middle ear is the vibration of those sounds start to vibrate tiny little bones. Those tiny little bones, the hammer, the anvil, and the stirrup. This is a really good trivia fact. They're actually the 3 smallest bones in your body, the hammer, anvil, and stirrup. Finally, once your middle ear is vibrating, those little bones vibrating, those vibrations translate to electrical impulses in your inner ear. A lot of this happens in the cochlea, sometimes called the cochlea. The cochlea or cochlea is going to translate those vibrations to electrical impulses that your brain can read. So at this point, let's zoom in on that cochlea a little bit more. First of all, it looks like a snail. It is filled with fluid. So this is your inner ear fluid. If you've ever had like an earache, I know I'm thinking back to my childhood when I was a gymnast. When I had earaches, my balance was always really off when I went to gymnastics. And that was because the inner ear fluid was, infected, kind of messed up. That's responsible for your balance. Cochleas are really, really small. So they would be about 3 centimeters long if you took it and you stretch it out. So right now it's all coiled up, but if you were to kind of unroll that snail, only 3 centimeters long. And inside there are about 20,000 hair-like nerve endings. And each of those little nerve endings will vibrate according to an incoming sound wave. So here's where those vibrations are getting translated into electrical impulses. Now, each nerve hair, per se, is sensitive to a particular frequency, a particular pitch. So, for example, the hairs over here, if you look at my cursor, are sensitive to like 5,000 hertz, a really, really high pitch. Versus in the center, you'll see like 400 hertz, so that would be a really, really low pitch. So your cochlea's nerve hairs can wear down over time. So on the left here, you see a good cochlea. This is a healthy cochlea. On the right, you see a not so good cochlea. You'll notice that all the little hairs that you used to be able to see, you can't really see them anymore. Some of this happens naturally just as you get older, your hearing gets worse. You may notice that when you're talking to grandma and grandpa, that both volume, so you have to speak louder, and pitch and frequency, like men's voices tend to be a little bit easier to hear for older people because they're lower frequency. So both of those can start to go as you get older. Something that's really concerning for our generation is we now have earbuds that we kind of shove into our ear and funnel a lot of that sound straight into our ear. So there's a lot of concerns that in the future, as we get older, our hearing is going to go quicker because of that. Here is a YouTube. If you would like to watch that YouTube is going to be of a baby who was born either without a cochlea or some sort of defect in the cochlea. And what they've done is given her a cochlear implant. So the video captures the first time that they have turned this implant on. So essentially the first time that this baby has heard sound. It's a really incredible video. I also included this link here so that you can test yourself. So this will play different frequencies, and you can see which frequencies you can personally hear and which ones you already can't hear. And so it's happening. Your hearing is getting worse over time. So the next part of this lesson is to pick up the fun hearing facts sheet and do a quick read through. We've covered some of those facts already, but there are a lot more interesting facts to read about there.